It's wonderful to be here. Today I'll be telling you about some of my work on how desires and wants might bias perceptual decision making. As many of you probably know, we're in the middle of a World Cup. So I thought I would start with some World Cup trivia. So the 1966 World Cup was played between England and West Germany. It was a tightly contested match, and the two teams were tied 2-2 going into extra time. And this was when England led a counterattack on the German goal. And so here's England playing in red, crossing in from the flank, taking a shot at goal, hits the crossbar, and the ball bounces away. Let's take a look at that again in slow motion. Did the ball cross the line? This has turned out to be one of the most disputed questions in World Cup history. So the English commentator thought that it did. His German counterpart was less sure. The English player was certain that it went in, and the German player was equally certain it did not. And so maybe they were looking at this from different angles. What about people watching the same video on YouTube? Turns out they didn't agree either. So what could be going on here? Why is the same visual information giving rise to systematically biased perceptual judgments? One possibility is that one group of people are lying. Another more intriguing hypothesis is that perhaps wanting to see an outcome can bias people towards seeing it. So we know there is a wealth of research on how people make perceptual decisions. The sort of canonical story is that perceptual information from the visual world is processed in sensory areas in the brain. The sensory evidence is integrated in higher order brain regions that then gives rise to perceptual responses. So in the study I'll be talking about today, I'm interested in studying how wanting to see an outcome can bias perceptual decisions. To do that, we presented participants with ambiguous images created by morphing faces and scenes together in different proportions. And participants' task was to indicate whether they saw more face or more scene in the image. And they were rewarded for each correct classification. At the beginning of each trial, we motivated participants to want to see a particular category. So to motivate participants to see more scene, we told them that they will win extra money if the upcoming image has more scene, or that they will lose some of their earnings if the upcoming image has more face. And to motivate them to see more face, we told them the exact opposite. Crucially, this additional bonus or loss depends only on the objective category of the image and was independent of participants' subjective categorizations. So to earn the most money from this task, participants should ignore this irrelevant information and make the categorizations as accurately as they can. Nevertheless, participants might be biased by what we motivated them to see. So plotted here is the psychometric curve when participants were motivated to see more face. When participants were motivated to see more scene, the curve shifts left, indicating that at each face scene proportion, participants were now more likely to indicate that they saw more scene. As I mentioned earlier, this motivational bias is suboptimal, and true enough, participants who performed, who were more biased, whose categorizations were more biased by motivation, performed worse on the task and earned less money. So these results provide behavioral evidence that motivation can bias perceptual judgments. It doesn't really say very much about the process by which it happens. So to start to get at this how question, one approach is to use computational models. So many of you probably are familiar with drift diffusion models. They're commonly applied to study perceptual decision making. They assume that perceptual decisions arise from the accumulation of sensory information towards a decision threshold. And we can model this process as a diffusion process starting with starting point Z. And at each time point, we assume that participants sample noisily from the stimulus. And when the level of evidence reaches a threshold, a decision, in this case the one foreseen, a decision is made. The rate of evidence accumulation depends on the drift rate V, which is determined by the amount of sensory evidence in the image. So if an image has a lot of scene, V will be highly positive and evidence will accumulate very quickly towards the scene threshold. What this model provides us with is a framework by which we can formalize the process by which participants make their perceptual decisions. Within this framework, motivation can bias perceptions in two ways. Firstly, it can bias the drift rate such that evidence accumulates more quickly for the category participants were motivated to see. You can think of this as a perceptual bias because it assumes that the way in which sensory information is processed has now been changed. On the other hand, motivation can bias the starting point by moving it closer to the motivation consistent category. This instead reflects a response bias because it reduces the evidence needed to respond in a particular manner without actually changing how sensory information is processed. We can estimate values for these parameters by fitting the data to participants, by fitting the model to participants' data. And what I plot here is the posterior distribution of posterior distribution for the estimate of the mean drift rate when participants were motivated to see more face. When participants were motivated to see more scene, our estimates of the drift rate was higher, suggesting that sensory accumulation was indeed biased towards accumulating faster for scene-related information. The similar pattern is observed in the starting point, such that the estimate of the starting point is closer to the motivation consistent category. Taken together, what this modeling result suggests is that motivation biases motivation biases reflect both a perceptual bias as well as a response bias. Of course, believing in these results require you to buy into the assumptions of the model, which you might not, and that's perfectly reasonable. What I hope to do next is to look into the brain and provide converging evidence for these claims. So the model suggests that motivation biases sensory processing. This is a hypothesis we can directly test by looking at sensory evidence in the brain. So we train a classifier in a localizer task to recognize patterns of brain activity that were selective to faces and scene. We can then apply this classifier to the task data to quantify the level of face and scene evidence on each trial. Here I show the level of scene-related activity when participants were motivated to see more face. When participants were motivated to see more scene, the level of scene-related activity was higher at each face-scene proportion, suggesting that motivation indeed biases perceptual processing. We can quantify this neural bias for each participant and test to see if it's related to the estimates of bias that were estimated by our computational model. And here we show that the bias in sensory processing in the brain was associated with model estimates of the bias in drift rate, but not model estimates of the bias in starting point. Where might the bias in starting point be implemented in the brain? One candidate structure that's come up before in an earlier talk is the nucleus accumbens, which has been associated with reward and reward-seeking behavior. Consistent with this idea, activity in the nucleus accumbens was higher when participants made motivation-consistent categorizations. I don't have time to show you the data here, but these results do also come through in the whole brain search. Perhaps more importantly, we also found that this increase in nucleus accumbens activity precedes image onset, suggesting that it's preparatory activity and not a reward response to seeing what one wants to see. So we can take the nucleus accumbens activation and test to see if it's associated with model estimates of the bias. And here we show that the nucleus accumbens activation was associated with the starting point bias and not the drift bias. So taken together, what these data suggests is that motivational influences on perceptual judgments compose or reflect both response bias associated with anticipatory activity in the nucleus accumbens and a perceptual bias that's related to biases in the sensory processing in the ventral temporal cortex. So in the remaining minute or so that I have left, I thought I would I would talk about some ongoing work. So motivation is often associated with heightened states of arousal. Just imagine a World Cup match. We're interested in to see how arousal might be related to the decision biases that we see in our task. So as mentioned in the earlier talk, one way that we can start to look at arousal, and it's more specifically norepinephrine, is to measure pupil dilation. So we're measuring pupil dilation as participants are performing this task, although in this case, we're actually predicting that higher arousal might give rise to more bias. Another thing we're trying to do is to use mouse tracking to start to examine the temporal dynamics by which motivation acts on perceptual decision making. So I think the data today I presented today suggests that wanting to see an outcome can bias what people see. Of course, this is just one study, and I think a lot more work needs to be done to test the robustness of this effect. What I will say though, With events such as the World Cup, it's mostly fun and games. At least it's mostly fun and games for most of us. But there are many cases in which motivational biases in decision-making can have more serious consequences, such as eyewitness testimonies. And I hope that what I presented today provides a starting point to start to examine some of these other scenarios. With that, I want to thank my advisor, Jim Yozaki, my collaborators and funding agencies, the organizers for this wonderful opportunity, and thank you for being a delightful audience. Thank you.